Okay, so the remaining concept for Lewis structures is the concept of resonance structures and electron delocalization. So you may have seen in some of our drawings when we've been doing Lewis structures that sometimes there's more than one equivalent Lewis structure that can be drawn for a species, whether it's a molecule or a polyatomic ion. So SO2 is a good example of this. If you're drawing this and you're following the octet rule, then you'd see that each of these atoms needs 8 electrons, so that's 24. They each come to the table with 6, so that's 18. And therefore, the difference is 6, which equals 3 bonds. So you've got 2 oxygens to bond onto, you've got 1 sulfur that you're going to put in the middle, and you've got 3 bonds. So that means 1 bond to one of them and 2 bonds to another. That's really all you can do. And then if you give lone pairs to you give every atom an octet, you end up with this structure here for SO2, and it's a perfectly valid Lewis structure drawing that obeys the octet rule. However, there's no reason why you couldn't have drawn the 2 bonds on the left side and the 1 bond on the right. And it doesn't really matter which one you draw, they're both correct, and they're both possible. All right, now, when you have these 2 equivalent Lewis structures that are possible, and you draw them both, they're known as resonance structures. So resonance structures are equally valid Lewis structures that illustrate the multiple possible positions for these extra bonds between certain atoms. So this extra bond is really the bond that can have more than one position. The single bonds are set in stone. You have to connect the oxygens to the sulfur if it's going to be an SO2 molecule. So really what the resonance structures are concerned with is this extra bond. It can be to the oxygen on the right, or it can be to the oxygen on the left. So there's 2 possible positions, at least while we're obeying the octet rule, where this extra bond can go. For HL, there actually is an additional structure that you could draw that breaks the octet rule. But for SL, there's only 2 positions where it can exist. And so whenever you draw these equivalent Lewis structures, and sometimes there's more than 2 equivalent Lewis structures, you show that they are resonance structures by drawing a big double arrow between them. So this is a messy big double arrow, but that's what I'm starring down here. It's something that people often forget, or they draw an equal sign between the resonance structures. The convention is a big double arrow goes between resonance structures to show that both of these structures are possible. So that's all resonance structures are. When you get Lewis structures where you can put extra bonds, the double bonds, the triple bonds, in more than one position, actually drawing out all those different positions and connecting them with double arrows, that is drawing resonance structures. Okay, but it turns out that both of those resonance structures are not actually the truth about what SO2 really looks like or really behaves like. It's one way to sort of explain resonance, to think about it is like if you had these 2 structures flipping back and forth between the double bond on the right and the double bond on the left. But what they actually see when they observe SO2 and they take measurements of it is that you don't have one long single bond and one long double bond, and then you don't see that flipping back and forth. What you actually see is that both bonds between the sulfur and both oxygens are equal in length and they are equal in strength. And both lengths and strengths are in between that of a single and a double bond. So it turns out what actually happens is that extra bond, those electron pairs, actually is delocalized across all of those relevant positions that we were talking about. And that spreads out that extra pair of electrons, and it makes everything more stable. And so you can't really draw this with a traditional Lewis structure, so you won't really be asked to draw these on the exam, but more conceptually, you need to understand that this is actually the truth about how this molecule exists. So here's the sulfur, and here's the oxygen, and here's the oxygen. And so instead of thinking of that extra bond as either being on the left or on the right, we're going to think about it as sort of being half on the left and being half on the right. And so these dotted lines, as messy as my drawing is, I apologize for that, that represents the delocalization. So that whole dotted line here, this is delocalization. So the only time we've really used that expression before is when we talked about metals. We talked about electrons being delocalized throughout the lattice of positive metal ions. But now we're going to talk about electron delocalization with covalent. Electrons can go anywhere. It doesn't mean this thing is going to conduct electricity. It just means that those two electrons, that electron pair that we were drawing in two positions, is actually spread across all three of these atoms. Okay, and that makes the structure more stable than if it had a double bond and a single bond separated. Okay, and it's based on different pieces of evidence. The bond lengths are not as short as double bonds. They're not as long as sulfur to oxygen single bonds. They are somewhere in between. And the bond strengths are also weaker than S to O double bonds, and they're stronger than S to O single bonds. So there's a lot of physical evidence that can be measured. The bond lengths and the bond enthalpies. Bond enthalpies are more or less a measure of bond strength. So they're pretty much equal to 1.5 bonds. There we go. Okay, and so bond order is a term called bond order. It's sort of a quantitative way of describing that idea, that actually the bond length and the bond strengths, bond enthalpies of these S to O bonds can't really be described as a single bond or a double bond. So a bond order is a way of saying, well, this bond sort of acts like it's got 1.5 bonds worth of strength and length. The way that you could calculate a bond order is pretty straightforward. If you look at the Lewis structures, in between the S's and the O's, these relevant atoms, we've got 1, 2, 3 bonds, the 2 single bonds and the 1 extra bond, and that is being spread out over 2 different locations. So 3 bonds, and there's 2 locations. Well, that equals 1.5. So that means that our bonds, we would predict that they would be about the length, halfway between the length of a single and a double bond, and that the bond enthalpies would be about halfway between the bond enthalpies of a single and a double bond for sulfur and oxygen. To see another example that has more than 2 resonance structures is the carbonate polyatomic ion. The double bond can be in this position, on the left, or at the bottom. All 3 are equivalent, all 3 are valid. Any one of them would count as a perfectly legit Lewis structure with the brackets and the charge on the outside. So the double arrows connect the 3 resonance structures, and that's what you would draw if you were asked to draw the resonance structures of carbonate. This is a representation of the resonance hybrid. Again, you probably won't be asked to draw this. It's more conceptually understanding that that extra bond is actually spread out evenly amongst the 3 carbon to oxygen bonds. So that's the electron delocalization. The bond order, if you look at the Lewis structures, there's 1, 2, 3, 4 bonds between the carbon and oxygen atoms, but there's only 3 different places. There's 3 different carbon to oxygen bonds there. So 4 bonds spread out over 3 locations. That means, whoa, sorry about that. That got a little messy. That means that 4 divided by 3 is approximately 1 1/3. So we'd say the bond order is about 1.33 approximately. So we'd predict that the bond lengths are about, closer to the length of a single bond than a double bond, and the bond enthalpies would be closer to the strength of a single bond than a double bond, but a bit stronger and a bit shorter than a single bond. And that's really the concept of resonance, the idea that these extra bonds, rather than flipping between equivalent places, are actually spread out evenly delocalized across all of these equivalent positions. That makes molecules and polyatomic ions more stable, and it results in their bond lengths and bond enthalpies being in between that of single and double bonds. We can quantify that with a value called the bond order.